Hello everyone, welcome back to part 3 of chapter 25. And we're done with the derivations for the different types of capacitors. We saw the parallel plate, the cylindrical and the spherical cases. And so now what we want to do is we want to take what we know about the capacitors and this ratio of charge to potential, which we started using to define the value of the capacitor. We then used this equation to derive the physical parameters of those different types of capacitors. And so what we need to do at this point is see how these capacitors are going to behave in a circuit. And we've already seen the symbol for a capacitor in a previous video here, and that is just going to be the parallel plate. And we're going to use this symbol regardless of the type of capacitor that we're using. Again, there's all different kinds of capacitors with different geometries, but we need something consistent that we can use in our circuits diagrams, and this is going to be that symbol. And so C is how we're going to represent the capacitor in our equations. The farad is the unit for the capacitor. And the next thing we need for these circuits, we're going to need a source of electric potential. And so that's going to be the battery symbol, similar to the symbol for the capacitor, except one of the plates has to be larger than the other. And it is the large plate that carries the positive potential for that battery. And since the battery is providing the voltage, this is our electric potential source. And we've got volts for voltage, obviously. Some other symbols that we're going to see in these circuit diagrams. We have this one, and this is a switch. And there's two different ways that you can draw the switch. You can draw it open, which is what we have in this first picture. This is an open switch, and this is a closed switch. And you can think of a switch like a drawbridge. If the drawbridge is open, then the troops can't get across. If the drawbridge is closed, then your troops can get across. Well, in this case, the troops are going to be the charged particles. And if I have a charged particle that I want to move through the circuit, well, the only way that we're going to be able to do that is if we close that switch and provide that full connection or that full path. Otherwise, if the switch is opened, we don't have a path that the charge can follow. And these switches, as we open or close the switch, by either allowing or denying the charge that path of motion in the circuit, can cause a lot of changes in the way that we represent the math for that circuit. And then some other symbols that we're going to see, or that we could possibly see in these circuit diagrams. There's a symbol that looks like this, and this is what we call our ground. And so in this case, we would have a 0 volt or 0 potential. And this is basically just our way of controlling the electric potential at a given point in the circuit. It's also a safety consideration, because if we get too much electric potential or too much charge in a circuit, then we run the risk of an electric discharge or a damaging a portion of the circuit, or maybe even harming someone who's using that circuit. So if we see this symbol, that means that that portion of the circuit is grounded. Some other symbols that we'll see along the way in the next chapter, we're going to start working with resistors. And so a resistor is going to have this zigzag pattern. And then in the very last chapter, chapter 30, we'll start working with inductor coils. And inductor coils, they look similar to a resistor, especially if you draw them really fast. If you're too sloppy with your drawings, resistors can sometimes look like inductors, but the inductor needs to look like a coil. You need to have loop after loop after loop. With the resistor, it's just the zigzag motion. And we will use R to label resistors in our circuits. For the inductors, we're not going to use capital I. We're going to save that for a different term. We'll get to that when we get to those chapters. But for the inductor coil, we're going to use L for the value of the inductor coil. Again, we'll revisit a lot of these symbols and terminology when we get to those specific chapters. But for right now, these should be the ones that we see here in chapter 25. And so let's start with an example problem. We're going to take a battery of potential V, or voltage V if you prefer, and we're going to connect it to a capacitor C. The capacitor has a value of 200 microfarads, and I think we already did an example problem like this, but I'm going to choose a 9-volt battery to hook this capacitor up to. And what I want to know is how much charge is going to be stored on that capacitor. So we go to our capacitor ratio equation. We will rearrange to solve for the charge. The capacitor has units of micro, whereas the potential just has units of regular volts. And so when we multiply these terms together, we will get an outcome that is dependent on that micro. So in other words, we'll get microcoulombs if we just multiply the two values together. And so 200 times 9 is going to give us 1800. So 1800 microcoulombs. From there, you can rearrange the decimal placing and whatever script that you want to put on the unit there. But this is just far easier to work with in terms of the math. Okay, so what if we have the same capacitor, but we hook it up to a different battery, and the charge that we see deposited onto that capacitor is 2500 microcoulombs? What was the voltage of this second battery? We'll call it V2. So up here we've got V1. We want to know what V2 is. So again, we go back to our capacitor ratio expression. We're going to rearrange for V, and that's going to be Q over C. So we need the charge of 2500 microcoulombs divided by the capacitance of 200 microfarads. Now again, we can take advantage of the units because we have micro divided by micro. each of those units will have a 10 to the minus 6 attached to it, but we're dividing those out. So we now have 2500 divided by 200, which is 25 over 2, or 12.5 volts. That was the value of the second battery that we hooked everything up to. All right, that's about it. That's about all we can do with a single capacitor. So now we want to see what happens if we have more than one capacitor in our circuit. And there are multiple ways that we can connect the capacitors to one another. And the two major case scenarios are series and parallel. And we will look at each of these cases in depth. For series, we have to connect one after the other, or end to end. And so this means we have one capacitor, which I will call C1, connected to a second capacitor, C2. So one C2, sorry. So one capacitor connected to the other, end to end. And then we can later connect that combination to a battery, and we'll see what happens. But then we've got the parallel case. With the parallel case, the capacitors need to be connected head to head and tail to tail. So here we have capacitor 3 and capacitor 4. And the heads of the capacitors need to be connected. So I'll put a wire between them. And the tails have to be connected. From there, we can then connect to a battery and see what happens. So we're going to start with the series case scenario and see what happens with these capacitors, and also see if we can put together some math to describe what's happening with these capacitors. So capacitor 1 and capacitor 2. I want to give these different values just so we can distinguish between the two. We'll let capacitor 1 be 100 microcoulombs, capacitor 2 can be 200, and we're going to connect them to a battery of, we'll say, 30 volts. So what's going to happen? Well, we're going to start working under the assumption that both of these capacitors are empty. We've gone to the store, we've purchased them, and neither of them have any charge stored on them, which is actually a good thing, because if you have a capacitor that's charged up and then you go and you try to pick it up, you can end up having that capacitor discharge and you can get a nasty shock. So both of these capacitors are empty, and that means that for each capacitor, we have zero charge, but that doesn't mean that the capacitance is equal to 0. If I have zero charge, then the potential difference across those capacitors currently has to be 0. And 0 divided by 0 is technically undefined, but undefined just means that you can have a lot of different possible answers. But we know that each of these capacitors has a rated value. But we're going to change that because we're going to connect our system of capacitors to this battery. And the battery has all of these positive and negative charges that would like to come out and play. And so the positive charges are going to come out of the battery, and they're going to find their way to the top plate of that first capacitor, and they're going to start spreading themselves out until they can't fit anymore. So there comes a point where there's so much positive charge sitting on that plate. And remember, the positive charges don't like each other. And so there's all of these other positive charges that are sort of waiting in line to get to the capacitor, and the charges that are already there are saying, nope, stop, we're done, we're full, nobody else can come in. All right. So let's clean this up a little bit. At the same time, we have negative charges that go and spread themselves out across the bottom plate of the second capacitor. And the same thing is going to happen down here. We'll eventually get to the point where we have so much charge that is built up on this bottom plate that those charges say, nope, we can't have any more negative charges come in. We're full. And it is at this point that the top plate and the bottom plate have their respective equal and opposite charges. Now, why do these charges have to be equal and opposite? Well, because they're coming from the same battery. The battery has to be able to give up equal amounts of charge. Otherwise, if it doesn't, then the battery is holding on to an uneven charge amount. And that's not going to be good for the battery. The battery could end up getting damaged if that were the case. Well, so we've got charge on the top plate of the first capacitor, and we've got charge on the bottom plate of the second capacitor. But what about the bottom plate of capacitor 1 and the top plate of capacitor 2? And if you notice, they are connected by a wire, except they're not connected to anything else. Essentially, the bottom plate of capacitor 1 and the top plate of capacitor 2 are forming this island of conducting material that is completely isolated. It's not touching anything else. It's just sitting out there. And the question that I have is, how much charge is on this island? And most people would look at that and they would say, well, there's zero charge. And that is technically correct, because there is a null charge or a net charge that is equal to 0. But that doesn't mean that there are not positive and negative charges on that isolated island. What this means is that we have equal and opposite amounts of positive and negative charges on that island. And they're currently happy because all the positive charges and all the negative charges have paired off, and they've produced the null charge. But now there's this huge concentration of positive charges above the island, which is going to start attracting the negative charges that are currently occupying that island. So we're going to see some of the negative charges from the island migrate towards the top. And at the same time, all of the positive charges that are on the island are going to be attracted to this large concentration of negative charges below. And so our null charge splits. It deviates into two groups of equal and opposite charge amounts, which just happens to be negative Q and positive Q. And what we now have is the first concept that we need towards working with series capacitors. If we look at the first capacitor, the charge values on the top and bottom plate of that first capacitor are plus and minus Q, which is exactly how we were working with capacitors when we were going through those derivations. And at the same time, the charge values on the plates of the second capacitor are also positive and negative Q. And so what this means for us is that capacitors, I'm going to write caps for short, capacitors in series will have the same charge values. Capacitor 1 is holding a charge magnitude of Q. Capacitor 2 is holding a charge magnitude of the same Q value. But they will have different what? Well, we can already see that they're different values of capacitance. But if you have two capacitors of different values, but they both have the same charges, then the only outcome is that they have to have different potential values. So capacitor 1, if we put some subscripts to all of this, capacitor 1 will have some charge on its plates, and there will be a potential difference between the two plates that we call V1. Capacitor 2 has the same charge, so Q1 is equal to Q2, and we might as well just call both of them Q so that we don't get ourselves confused here. But capacitor 2 is going to have a different potential difference between its plates. And we can now express what those two different potentials are going to be. The problem is that I don't know how much charge is going to be deposited onto those two capacitors. I know that they're going to be the same amounts, but I don't have a number for them yet. And even though I have the potential of the battery that's connected to the system, the potential of the battery is not going to be the same potential that we see across capacitor 1 or capacitor 2. And we should talk about that. See if I can get rid of that. Well, I'll just have to redraw it then. So let's talk about potential and potential difference. On either side of the battery, we're going to consider these 2 points. And the potential difference across those 2 points is the potential of the battery, 30 volts. Now, to get that potential difference of 30 volts, we would have to travel from one point to the other. remember with potential difference, we had to actually travel through the system to account for that potential difference. Okay, so I have to travel from one side of the battery to the other to account for that 30-volt potential difference. All right. Well, do I have to take this route? Or could I take this route? And the answer is sure. If you wanna take the longer road, you can do that. You can still get between those 2 points. But regardless of the path that you take, you still have to account for the same potential difference of 30 volts. By taking the longer route, you are going across the first capacitor, which has a potential of V1, and then you go across the second capacitor, which has a potential of V2. But what's the difference between, get a different color for highlighting here. What's the difference between this point and this point on the circuit? There is nothing between those 2 points except for a wire which is being used for the connection. There is nothing between those 2 points. In fact, this wire is just one huge point of connection between the battery and the capacitor. Likewise, what is the difference between these 2 points? And again, there is none. All we have in between the battery and capacitor 2 is a wire connecting them, and so everything there is basically just one big point of connection. So if this point is the same as this point, and this point is the same as this point, and we're getting 30 volts potential difference between those, then we have to be getting 30 volts potential difference between those. Well, what's between these 2 points? It's the combined potentials of the 2 capacitors. This means we can put the information together into an equation, and I am going to redraw our capacitor system down here just because the top picture is getting kind of messy. All right, so there is a potential difference across capacitor 1. There is a potential difference across capacitor 2. They both have the same charge, but we can now see that the potential difference across the battery has to be accounted for with the combination of the potentials that we get passing over each capacitor. Well, we can do something with this. We have these equations here that tell us what the potential for each of those capacitors should be. We have the unknown charge and capacitor 1. We have the unknown charge and capacitor 2 equals the known potential of the battery. And from here, we can factor out the unknown charge. We can plug in the values of each capacitor, 100 and 200 respectively. 1 over 100 plus 1 over 200. That's going to result in 3 over 200. And so now we can solve for the amount of charge that will deposit onto each of those capacitors. We just need to multiply by the reciprocal of our 3 over 200. So that's going to be 30 times 200 over 3. It's going to make 10. 2,000. And the units, remember that the units for our capacitors are in microfarads. We've got regular volts for our potential, and so we're going to end up with microcoulombs for the charge. So each capacitor will have 2,000 microcoulombs deposited onto it. How do we check our answer? Well, you can plug those back in to the individual expressions. If we have 2,000 microcoulombs deposited onto capacitor 1, 100 microfarads, well, that gives us 2,000 over 100, which is 20. And then 2,000 over 200 is going to equal 10. All right, so the potential across capacitor 1 is 20 volts. The potential across capacitor 2 is 10 volts. If we add them together, we get the 30 volts from the battery. So everything is fitting together perfectly. But this could take a while if we had more than 2 capacitors connected in series. And it is possible for more capacitors to be added in series, but that would just mean that we would have to add all of their potential values sequentially to account for the total potential that's coming from the battery. And that's going to take too much time to go through and solve. But there is a shortcut that we can take. Right about here, I want to make a slight alteration to the approach in the math. So we have our voltage summation expression here. And what I would like to do is I would like to see if there is an alternative to using the 2 capacitors. And by alternative, I mean, is there some other capacitor in existence that I could use and accomplish the same job as what these 2 capacitors are doing together? And we would call this the equivalent capacitance of the system. Well, what do we mean by doing the same job? Well, I mean, can we pull 2,000 microcoulombs from the battery? Because that's what we did in the case of capacitors 1 and capacitor 2. We pulled 2,000 microcoulombs from the battery, and that charge deposited onto the top plate of the capacitor. We also pulled negative 2,000 microcoulombs, which deposited onto the bottom plate of the second capacitor. And then we had our island scenario where the null charge on the island split up to give us our positive, negative pairing to produce our plus and minus Q values for the capacitor system. So, is there a single capacitor out there that could do the same job? And we would say, well, let's take the capacitor ratio equation and let's find out. We know what the necessary charge value is, so we're kind of cheating by putting that in here. But we've got 2,000 microcoulombs over 30 volts. And so we would have to have a equivalent capacitance of, let's see, 200 divided by 3 is not going to turn out pretty, but that is what, 66.7 microcoulombs. That would be the equivalent capacitance for this circuit. Well, how does that help us? Especially since we had to use that solved value of charge. Well, that's not what I'm really interested in. Yes, I want to know what the equivalent capacitance is, but I would rather use this bit of information. And I want to take that bit of information and plug it back up into that equation. Or more specifically, this equation right here. All right, we're going to put everything together now. The potential associated with the first capacitor is the unknown charge Q. Yeah, I know we know what it is, but we're going to pretend that we don't. Divided by C1. The potential of capacitor 2 is the unknown charge over capacitor 2. And that equals the 30 volts, right? Correct. But I'm not going to plug in the 30 volts. I'm just going to keep that as V. And then I'm going to use this expression. If the equivalent capacitance has to equal Q over V, then V has to equal Q over the equivalent capacitance. And the V that we're talking about here is the potential that is going to be placed across our equivalent capacitor. Well, the only thing that I have in that equivalent picture is the potential of the battery. So that potential, which is the potential of the battery, is going to go up into that equation. And look at what we have now. We have Q, we have Q, we have Q. Every term has the same Q value, which means none of them need the Q value. Well, I thought we wanted to find the charge. We do, but for now, we have a means of solving for that equivalent capacitance. We have an inverse summation here. We have 1 over the value of the equivalent capacitor is the summation of 1 over the individual capacitance values. So let's see what we get. We had 1 over 100 for the first capacitor, 1 over 200 for the second capacitor, and we've already done this before. This happened during this step right here. We were actually finding the equivalent capacitance without even realizing it. That summation is 3 over 200. And you're looking at that and you're saying, well, that's not that value, and I agree. It's the inverse value. We have to take our answer and we have to flip it over. The equivalent capacitance would be 200 over 3, which is 66.7 microfarads. Well, why is it helpful to find the equivalent capacitance? Well, for starters, you can perform this method of combining the capacitors without having to involve the potential of the battery or the charge on the capacitors. We can just combine them right away, and we can get an equivalent capacitance. Once you have that equivalent capacitance, you can now ask yourself how much charge is going to be pulled from that battery of 30 volts. And our equation says that for an equivalent capacitor connected to a 30 volt battery, the charge will be the product of the two, and I'm just getting that from our ratio expression. 66.7 microfarads times 30 volts. We multiply those together and we get 2,000 microcoulombs. So that is a much faster, far more efficient means of finding the charge that is going to deposit on each of these capacitors. And then if you want, you can go back and you can use your voltage summation as a self-check. We know that each individual capacitor will now have those 2,000 microcoulombs, and we've already gone through and we've done that self-check. We know that this is the right answer, but we now have a far simpler means of finding that answer. So let's see, where did we have our notes here? We said capacitors in series will have the same charge values, but they will have different potentials. And we can find the equivalent capacitance of those series capacitors by taking the inverse summation. We just have to remember to flip our answer over when we're done. All right, that is the case of the series capacitors. We now need to take a look at the parallel capacitors. So let's take this picture and we'll bring it down here. We'll zoom in a little bit. Capacitors 3 and 4. So we'll use different capacitors here. We'll say 300 and 400. And we'll use a battery of, let's say, 100 volts. I'm just throwing some numbers out there. Don't know how pretty or ugly these answers are going to be, but okay, capacitor 3 and capacitor 4 are connected in parallel, so their heads are connected by the same wire, and just like the discussion that we had above, this is all one point of connection between the two. And that means when we go to connect the tails of the capacitors, well, that's all one big point of connection as well. This brings us to our first concept for parallel capacitors. If these are both the same points, then the potential difference across capacitor 4 between the two ends of capacitor 4, that's the same as the potential difference across capacitor 3, because their heads and tails are connected at the same points. So in this case, both capacitors have the same potential value. Caps in parallel have the same potential values. But because they're different capacitors, they will have to have different charges. So time to figure out some values now. We have our values for capacitor 3 and capacitor 4. We know they're connected in parallel, and I'm going to connect that system of capacitors to our 100-volt battery. Now, if our capacitors are connected at the same point at the top, well, what is that point up here? Especially now that we can see that it is connected to the top of the battery. Well, we can now see that the head of each capacitor is connected to the head of the battery. And what about down here? What about the tails of the capacitors? Well, they're connected together, but that connection is connected to the bottom of the battery. So looks like both capacitors not only have the same potential, but they have the same potential as the battery. Now, please do not take this as a given in every scenario. Your parallel capacitors are not always going to have the potential of the battery. It just so happens that the battery is connected to the top and bottom of those capacitors. If I were to get rid of the battery entirely, well, those capacitors no longer have the potential of the battery, but they do still share the same common potential value. So that is a very important distinction to make. We're just using this for our initial discussion so that we have some numbers that we can work with. All right, well, if I know that both of these capacitors have the same potential and that potential is equal to the battery, then both potentials are equal to 100. And since I already know what the individual capacitance values are, I can solve for the charge that will be deposited on each of these capacitors right away. Now I'm gonna drop the subscripts on the V's because we know that they're both the same. To solve for the individual charges, this is going to be Q3 times V. Q3 was 300 microfarads. We've got 100 volts. 300 times 100, that's going to be, what? 30,000 microcoulombs. 1, 2, 3, 4. 1, 2, 3. Yep, 4 zeros. Okay. So 30,000 microcoulombs if you want to pare that down with your decimals and your scientific notation, you can do that. And then for charge 4, we'll have 400 microcoulombs and 100 volts, which is 40,000 microcoulombs. So why do we have different charges here? Well, is it just because the math says so? Well, let's see what it means in terms of the circuit. You're going to have 30,000 microcoulombs deposit onto capacitor 3. So I'm just going to write charge 3. And you're going to have 40,000 microcoulombs deposit onto capacitor 4. Where did those charge values come from? Where did those capacitors get their charge? Well, they had to have gotten it from the battery. The battery is going to send a total amount of charge out to the circuit, but then there's this intersection right here where the charge has to decide if it's going to go to capacitor 4 or capacitor 3. We already know how much charge is going to go to each capacitor, so if each capacitor got its charge from the battery, this means that the battery had to provide both of those capacitors with their charge. And this means that a total of 70,000 microcoulombs came out of the battery. Now this was a very straightforward and easy problem, but only because we already knew what the potential for each of these capacitors was going to be. In some future problems, we're not going to have that knowledge, but we still need to be able to figure out the answers to these systems. The next thing we want to do is see if maybe we can reproduce the equivalent capacitance idea that we used for the series capacitors. We now have a system with parallel capacitors, but is it possible to replace capacitors 3 and 4 with one capacitor that will do the same job? And what do we mean by the same job? Well, what we mean is, can this new capacitor pull the same amount of charge out of the battery as what capacitors 3 and 4 did? So we know that the total charge that has to be pulled from the battery is 70,000 microcoulombs. We know from our ratio definition that actually this is ready to go. The 70,000 microcoulombs divided by the 100 volts would have to equal an equivalent capacitance of 700 microfarads. So, can you think of any way that you might combine capacitors 3 and 4 to make 700? And you're like, oh, I don't know. What if we try adding them? Good job. There we go. But that, that's way easy. We can see that relationship. If I were to ask you with the series case, can you think of a way that you would combine capacitor values of 100 and 200 to make 66.7? Well, then you might be scratching your head. You might have to try a few different combinations, but even if you were able to combine 100 and 200 in a way that made 66.7, how do you know that that's a valid representation of everything that we did here? Well, we needed all of this math to basically back up our claim that this was going to be the equivalent capacitance. So we need some math to back up our claim that all we have to do is add the capacitor values together to make the equivalent. And the way that we're going to do that, it's similar to what we did with the previous example, except I can't just say the potential of the battery is equal to the sum of the individual potentials, because that's not true. We already know that each capacitor has the same potential, and each capacitor has the potential of the battery. So I can't say that 100 equals 100 plus 100. That's not true. But what I do have is this equation right here. I have this equation that tells me that any charge that comes out of the battery has to be distributed between the two capacitors. So there's a good start. How am I going to get those values? Well, we already have them. That's kind of the hard part, is that even though we know these values, we don't want to use them just yet. We want to be able to reproduce those values. So how about if we take a step back and we use the expressions for each. We know that Q3 is equal to C3 times the common potential V. We know that Q4 would be C4 times the common potential V. And that has to equal 70,000, right? Correct, except you don't get to use that value. We're going to pretend we don't know what that value is. Well, how else am I supposed to fill in the gaps here? Well, go back to your picture of your equivalent capacitor. And how does your equivalent capacitor compare to the total charge that should be drawn from the battery? That total charge would have to equal the equivalent capacitance times the common potential. And here we have every term with the common potential V. And now we have exactly what we needed. We have the summation of the two capacitors equals the equivalent capacitance of the circuit. And so all we need is a direct summation of all of the capacitors, and that tells us what our equivalent capacitance will be. So again, this particular example was easier than it should have been, but that was because we already knew what the individual potential values had to be. In some future problems, you're not gonna know that. All you're gonna know is that the two potentials are equal, and you have to figure out from there what your equivalent capacitance and charge values are going to be. But as you can see here, that common potential canceled out, and so we didn't need to know it in order to find the equivalent capacitance. So very, very useful stuff. We've seen examples that involve two capacitors in each case. As it turns out, the math for these equivalent capacitance expressions are not limited to two capacitors. You can have as many capacitors as you want connected in parallel, and they will form an equivalent capacitance that is equal to their direct summation. You can also have as many capacitors connected in series as you want, and the equivalent capacitance that they make can be found using the inverse summation of all the individual capacitors. Okay, so now we go on to our homework. We do some problems. Some of them have capacitors that are set up in series. Some of them have capacitors that are set up in parallel. But what do we do if we have both in the same system? What do we do if we have a system that has both series and parallel capacitors? I guess we'll have to take this a piece at a time. We'll have to look at different segments of the circuit to see if any of these capacitors can be combined in series or if any of them can be combined in parallel. And basically we're going to condense this entire circuit down to a single equivalent picture. So can we take this picture and replace all of the capacitors in their combinations with one equivalent capacitor that'll do the same job? And if we can do that, then we can start reconstructing the circuit in its original form to figure out all the information about that circuit. And so I'll say this: when we go to solve circuits like this, we want to know everything. And by everything, I mean I want to know the charge that's associated with all of the capacitors. I want to know the charge that's coming out of the battery. I want to know the potential that's associated with each capacitor, along with the potential associated with the battery. And if we can find that information, we can answer anything about this circuit. So that's what we're going to do in the next video. We're going to look at an example problem similar to this. It is a bit repetitive. It's not difficult, but it takes time. And we have to be patient as we go through these kind of problems because every single bit of the math is connected to another piece of math, and it's like this huge Sudoku puzzle where everything fits in with everything else perfectly. And if we don't do things correct, then we're going to be lost at the end. So I'm gonna show you a nice way of keeping track of all of your values in your work so that you don't get lost in the process. But that is for the next video. We'll see you there.